we are absolutely delighted to have in this session, two presenters. Carol, I'm going to introduce Carol and Mickey just together right now, and then we're going to follow in order. Their work has been really led the way. We used it a lot in thinking about the modifications we were making and some of the modifications we would have liked to have made, but we're not able to. Carol is going to speak first. She's a professor at the University of Massachusetts in Boston. She was a member of a very influential NRC report, which came out as the volume Taking Science to School. And she's been doing both since the time our proposal went in and we started the work of our center, and then on through that, she's been doing wonderful new work on learning trajectories, and I think you'll be speaking about some of that today and looking at longitudinal trajectories. Mickey Chi is a foundation professor in the Mary Lou Fulton Teachers College at Arizona State University. She's also the incoming director of the Learning Science Institute there, and I believe you just this year, for those of you who are at AERA, you might have had a chance to celebrate this. She got the Sylvia Scribner Award. She's been doing work looking at how students, for many years, looking at how they learn difficult scientific concepts. And I think she'll be talking today about the importance of developing certain schema that help students understand emergent phenomena, which are very important in the middle school science, and they are not well prepared for that. She's also been doing work on defining levels of active learning and helping teachers understand how to engage students and move them through these levels to help enhance students' learning. So I'm going to get out of the way. I will get my presentation out of the way. And let Carol continue.
All right. Okay. Oops. Okay, so I'm going to switch gears a little bit to discuss some of the conceptual challenges about matter, because that's what I focus on, facing elementary school students. I know you're all about middle school students, and what's needed to help them meet some of those challenges based on some recent research I've been working on with Sue Dubler and others on an NSF-funded inquiry project. And I'll invite you to consider what taking a longer-term learning progressions view of how to overcome these conceptual challenges might add to our understanding, not only at the elementary level, but beyond. Okay? So briefly, the goal of learning progression is to try, as I understand it, is to provide a kind of coherent account of how ideas from a lower anchor, let's say kindergarten, could evolve over a long period of time, given appropriate instruction, to the ideas we hope they might be achieving by the end of high school, okay? The upper anchor, it's often called, and we want to try to have a connected path that is consistent with what we know about how learning occurs, all those good constructivist principles that learning depends on prior knowledge and assimilation. Okay, now, it assumes preschoolers have rich ideas that are quite relevant to learning about matter, but they are fundamentally incompatible with the scientist's views, so that the gap, both epistemologically and ontologically, between where they start and where we want them to end up is large, okay? For example, how are they going to engage with the idea that gases are matter, or atoms are the constituents of matter, all of the things you're talking about in middle school, if they're thinking of matter as something that you can see, feel, and touch, right? It's going to be a kind of, it's not going to make sense. So an LP answer to this puzzle is partly to assume we don't have to get there all at once, all right? We can take our time, and that rather we might try to work strategically to design foster a series of reconceptualizations, deep reconceptualizations, such as the one shown here, targeted for elementary school, in which students modify existing ideas and new ideas are introduced with each reconceptualization, bringing them conceptually closer to the scientific view while trying to preserve some coherence and increasing explanatory power, and even more importantly, that we're positioning them so now they're in a better place to make the next reconceptualization and the next reconceptualization, right? We don't have to get there all at once. Now, it also assumes that traditional instruction is often not that effective in fostering deep reconceptualizations, right? That often what happens is kids end up learning a lot of facts that either add to existing concepts or sometimes even worse, as people say, destabilizes them, and they start thinking it doesn't have to make sense, right? Which is not a good idea. So we'll try and talk about, and then you're still incompatible and you haven't closed the gap. Okay, so in the Inquiry Project, we wanted to know a little bit more about what reconceptualizations to target at elementary, how would you design instruction that would be different, how does that contrast with traditional approaches? Okay, and I'm going to be telling you a little bit about the comparative longitudinal study that was done as part of that project. It's a small-scale comparative longitudinal study. We worked with 2 schools, 5 classrooms. Control students were students in the same schools a year ahead who had just the same teachers, regular curriculum about matter, and treatment got a modified version of it. Okay? And I'll tell you more about the treatment curriculum shortly. And, okay, so I wanted to start by just identifying a few. This week, a 2-hour individual interview with these kids, lots of different tasks, multi-part tasks. But I just want to give you some examples of some of the conceptual challenges that they faced at the start of grade 3, based on our interview. Okay, one task was a matter, not matter sorting task. We had cards with words on them and just common everyday kind of words. And they were supposed to put them in the piles of things they thought were matter, things they thought were not matter, things they weren't sure about. It was fine not to be sure. And then we went through their piles and said, could you tell us the reasons? Why did you put these in the matter pile? Why did you put these in the not? Why were you not sure? If you were forced to choose, where would you put them? And so on. Okay, now we assumed, based on the literature, it wouldn't be obvious that solids, liquids, and powders belong with gases as a sensible, coherent group. That just doesn't seem to make sense. But wondered what alternative groupings they might form, what they would say about that. Okay, and one of the interesting things was we found out that actually you might think that they might at least form a coherent group of solids, liquids, and powders, but that's not the case either. So that, in fact, the difficulties they had go well before gases. All right. So there are many alternative groupings that they formed, but one interesting kind of grouping was many of the obvious instances, or things we might think of as more obvious instances of matter, they didn't think were matter. And so they had what I call underextension errors. So here are some examples. Each line is just an individual kid's pattern of judgment. So they might not include ice, but they'd include wood and dog, and might leave out sand. So that some of these obvious instances, the red things, weren't included as matter. Sometimes they combined them with overextension errors where they would include heat or light. Other times they only made underextension errors. But again, this was suggesting that to us, they're not really mapping the word matter onto something that is maybe a concept that includes all solids and liquids, right? That's just not obvious to them. Others had more systematic patterns where they did include all the solids, liquids, and powders, and some even began to extend it to include some gases. Okay? We also looked at the reasons, and looking at the reasons for their groupings, it highlighted the difficulties they had identifying common properties of matter. There were a whole bunch that couldn't think of any common properties for their grouping. Sometimes they came up with a totally irrelevant common. This is consistent with the fact that the groupings looked odd when you started hearing what they were thinking about, or what, is it important? Is it something you need or use? Is it natural or not natural? Does it have parts inside? Lots of different things that they were thinking about. Some of them gave perceptual reasons, things that you can see, feel, touch, which might be a sensible thing to hold solids, liquids, and powders together. And one of the things that we found was that only a very few were starting to mention any physical properties that go beyond perceptual properties, and that might potentially be things that not only apply to solids and liquids and powders, but also to gases and other things. Now this actually is very similar to A lot of what Ruth Stavey found in her work, she had longitudinal studies in Israel, grade 1 to 7. She found that by grade 7, very few could mention any common properties for matter. So it suggests to us that kids are facing a kind of, certainly a semantic challenge in knowing what this word matter means, right? Which is often not appreciated by the schools. They just assume if we throw out the word matter, they know what we're talking about. This has to be negotiated. I also think underlying it may also be a conceptual problem of actually recognizing or developing a concept of matter where it's an important concept to you, and that because it shares a bunch of properties and knowing about enough properties that characterize this set. I think for a lot of young children, the differences among materials, even solids and liquids, are much more salient and striking to them than any commonality. So we have a little work to do here. Okay, another task. I've done a lot. You give them a ball of clay, they say, sure, it weighs a lot, or it weighs something. We break off a tiny speck. How about this piece? Does it weigh a tiny bit or nothing at all, right? And what do 90% of them say? Nothing at all, okay. And give you a lot of reasons. You can't feel anything in my hand. It's too tiny to weigh anything, right? And of course, we do get some others making another argument, saying, well, of course it weighs a tiny bit because it's there. It has to weigh something. But again, that's not the typical view of where they're starting, which suggests another challenge facing them is to reconceptualize how they're thinking about weight. And moving it away from being centered on felt weight to be related to if you have some stuff or some amount of stuff there. Give you another third task. Another task probed whether they were making any differentiation between the weight of a whole object and the heaviness of the material the object was made of. Okay, so what we did in this task, we brought out cylinders made of 3 different materials, and we discussed with students the names of the materials they're made of, right? And talk a lot about all these different pieces, and we're labeling them and everything. And then we focus on pairs of same-size cylinders, and first we ask for the one made of brass and the one made of aluminum. Is one object in this pair made of a heavier kind of material or not? They think the brass is a lot heavier, right? Made of a heavier kind of material. And then we do the same, comparing the aluminum and Delrin, kind of plastic, and again, they conclude the aluminum is heavier kind of material compared to the plastic. And then we bring out 3 more pairs made of the same materials that they've seen before, but they're different sizes, and ask them a bunch of comparisons about those, okay? So for these 3 different pairs, so a teeny, teeny little piece of aluminum and Delrin, is one of these made of a heavier kind of material, right? And then small brass, large aluminum, and small and large aluminum. So what do we find? So most of them will say, they'll judge the objects that feel heavier are made of the heavier kind of material. Okay? And we're using the locution made of a heavier kind of material, folks, right? Which is actually a kind of thing kids make up themselves to start to talk about density before they have learned that word. In fact, kids invent kind of locutions like this. And they'll often say, well, these you can't feel at all, they're too light, you know, all that kind of stuff. Only 17% actually made correct inferences saying, well, of course, the aluminum is the heavier kind of material here, it's aluminum, and this one is sort of carrying it over, okay? So this suggests another challenge, right? And the challenge here is developing a relevant precursor concept for density, heavier kind of material, that's differentiated from the weight of the object. And of course, I think that's part of developing some explanatory account for themselves of why things weigh what they do in terms of what they're made of and how much of it you have and all of that kind of thing. And also, I think you might notice, although these 3 tasks are really, really different from each other, I think they underlyingly call on some interrelated ideas that need to develop for these kids. Okay, summary of our key findings here. So basically, there are 2 broad kinds of challenges. Reconceptualizing existing concepts to be more scientifically compatible, and then developing some new concepts like matter, volume, and density that are kind of missing at this point, and integrating them into their knowledge network. And it supports our idea that some deep reconceptualization is going to be needed. And my next slide just is to tell you, I've only skimmed the surface of this. We really think about this as a complex network with lots of interacting parts. That reconceptualization is going to be complex and long drawn because it depends upon building so many linkages between different ideas and contexts. There's not going to be a quick sell. Okay? So what are some of the implications if you're thinking about learning in this way? I'd like to introduce 3 assumptions that we want to play with a little bit in designing our curricula and our learning progressions work. One is that we need to focus on a broad network of interrelated concepts, not isolated concepts or topics. We have to identify rich entry points. Where are we going to get started? Where are we going to push on this network that we can start moving it forward by having them examine different relationships and then open the door enough that we can introduce some new ideas in. And finally, a multi-year focus, revisit concepts in new contexts, always focusing on multiple concepts at a time. So this slide just highlights some of the core concepts that were the focus of the inquiry curriculum. Across grade 3, 4, and 5, we had 1 unit each year, about 16 lessons in all, just to give you a sense of the scope. Core concepts remain the same, right, across these units, something that they don't typically do, right, we go on to something else. But different ones get highlighted or foregrounded, so 2 might be in the fore at 3rd grade, another one comes into the fore, and also we're starting to sneak other ideas in here into this network. And just to give you an idea, the grade 3 investigations, we entered this centering on everyday objects and that have density cubes. And ideas about material and weight were foregrounded. Actually, they're very salient when you look at these density cubes. They're made of different materials and they're very different weights from each other. And it brings up a host of questions. We could compare the weights in different ways. You could compare them using your hands. You could compare them on scales. You could work to develop measures. Lots of interesting comparisons. And we would differentiate some differences between felt weight and scale weight, actually, as part of this. And they explicitly contrasted that, and they represented differences. They had visualizations in here. They also contrasted size and weight. Hey, these have the same size, but they're different weights, and started to use strategies to develop measures of size as well, or volume. In grade 4, we extended investigations to granular and liquid materials. We were expanding the scope, but we were actually saying, hey, look, we have little pieces. They weigh something too. They have a volume. We actually got into a lot more detail about more complex ways of measuring volume using liquid displacement. Of course, then the big thing is, which is relevant to liquid displacement, weight or volume? I mean, all sorts of interesting issues. And then in grade 5, we extended investigations to gaseous materials with a central focus on material, this time water, in its various transformations. But now weight played a new role as evidence for the existence of stuff, even when it wasn't visible. Okay, but we've been preparing the ground in many, many ways for this kind of culminating achievement. Okay, well, let me give you a quick sense of some of the findings, because I'm running out of time. I'll go through this kind of quickly. I'll give you findings on the 3 tasks that I already told you about, okay? What changes did we see among the inquiry students? By the end of grade 3, they'd made a huge leap in their understanding that those tiny little pieces weighed something and took up space. It was a direct target of instruction in grade 3. It's no mystery, except I think they were conceptually prepared to understand it. It's something that if you push on, they give. Only most of the time, nobody even thinks to ask them about this. Okay? So sometimes easy, low-hanging fruit just gets bypassed. Remember, they've been learning to measure, comparing felt weight, so we were actually having to engage them in a variety of arguments to convince them of this. You know, there's different, sometimes felt weight isn't accurate, and there are scales of different sensitivities, and we had thought experiments. If something weighed nothing, how could you add up all those pieces and get to something? Or we had real experiments. Let's have a piece of paper and another piece of paper and another piece of paper. Eventually you could feel it, but originally, so we did a lot of different things to engage them with this issue, and they actually found it very intriguing. It was a live issue for them. Another finding. Distinguishing weight of object from heaviness of size. This was slower but steady progress across the grades. You don't see as dramatic a rise. This was a case where we revisited this topic in a more sophisticated way. We just sort of got our foot in the door on heavy for size in grade 3. They were comparing same size things. Everything's confounded, really. By grade 4, they were starting to have different size samples and knowing more about volume. And you can see if we had flitted away from this topic, they might not have continued to make progress, but we had a chance for them to keep working on it. And so I think that shows why it may be important to revisit topics. And let me give you a third finding about how they're doing on sorting matter. Right? Finally, by the end of grade 5, we now see that most students seem to have a meaningful concept of matter that includes at least some gases, along with all the solids and liquids. So we're now starting to build a more coherent concept. And the majority also said, by the way, during the interview, that the matter takes up space and has some weight to it. We never got to, they're mentioning things like mass. Not surprisingly, the biggest shift in this came in 5th grade when they were we were introducing the word, discussing it in certain ways, but I think the fact that, again, they made the big leap meant we had been conceptually preparing them with a lot of earlier things that now they really were believing solids and liquids and even tiny, tiny pieces of those things had weight, so it didn't seem as big of a leap. Okay, what happened with the control students, the comparison students? In contrast, I think for these 3 tasks, what you're seeing is very little progress on these same issues for the control students. We might add that these students in their curriculum do explore water transformations, sometimes multiple times in each grade. Water transformations, they've been told solids, liquids, and gases are matter. In grade 3, now actually some sort of seem to pick up and believe it, but once you got the low-hanging fruit, nothing much happened after that, even with repetition. And I would suggest maybe one of the reasons that's the case is that the curricula aren't working on all those other things that we were working on, like tiny pieces have weight, and what's heaviness of kind of material, and all of those other supporting concepts that go into building that as a meaningful generalization about matter. Another kind of finding, there were a lot of relationships, interrelationships among different understandings, and interestingly, although they were not doing it as high a level in the control group, right, wasn't the majority understanding these things, same relations were often holding between the treatment and control group among tasks. And this is really important for us in learning progressions work because we sort of believe if you know about some of these intrinsic relations in the subject matter, these have to be built upon in the curriculum. So that's another idea to throw out. So let me just conclude with 3 implications that I think the learning progression approach might provide for thinking about how to overcome conceptual difficulties that's commonly overlooked the way a lot of traditional instruction is structured. First, we think it's really important to identify and develop important precursor concepts, not just final form ideas. This is big in learning progressions. You know, so much of curriculum is about just little pieces of the expert view, moving from that way. For example, many curricula commonly overlook the importance of developing students' ideas about weight, their ideas about material, their ideas about heaviness of material, because none of that looks like final form important for matter, yet we think that's preparing the ground for learning about matter. Secondly, I think it's important to work on constantly relations among concepts. I think you're hearing that as a big theme among other presenters as well, that are revisited in different contexts and across grades. Many of the curricula were commonly treating the topics that we were treating in isolation to the extent that they treated them. You learn about measurement and math, right? And sometimes people say, your curriculum's more about math, not science. Well, you know, some of these aspects bring to bear on science, and you can put them in that context, but if kids are experiencing them as separate silos, they're not building the connections, or they're not engaging in the arguments that make one thing that they're learning relevant to the other. And also, they often aren't revisiting them across multiple grades, right? You're flitting in, you did matter in kindergarten, we'll get back to it in grade 5, thank you. And I think it's also very important to think about what forms productive sequences for working on these relations. Again, we thought there were some early leverage points that have big payoff. Many curricula just pick something as their starting point, and it's too big a gap. So the water cycle is common kind of thing that, without worrying, are they conceptually prepared to really understand the powerful implications of that? So with that, I'll turn it over to the next. Well, I guess I'll take a few questions, and I want to also acknowledge, I was talking about the inquiry project. There's a fleet of people. It was not my project, but I enjoyed participating with them on the research team and thinking about some of these things, and of course other collaborators on learning progressions work.
You can take a few questions while we do it.
Okay. Yeah.
A quick question. Kids who say
that tiny things don't have weight. If you then give them and you give them 2 tiny things versus 1 tiny thing and ask them which one is heavier, would they say that the 2 tiny things is heavier than the 1 tiny thing, or
Not immediately or necessarily. I mean, I think when people hear about this, they think, of course, they could misunderstand the
Yeah, there's
question.
something
It
else.
must be some
It's something else.
superficial little thing that you could clear up
Yeah,
quickly.
okay.
This was a live issue for them, and they were engaging in debates, and really open. I think a lot of them aren't thinking about that, so that's certainly a good avenue into getting them to actually start to think about the problem in terms of, if you add all these things, where does the weight come from? So they can, and that begins to be compelling to them, right? Although they still have to explain, well, why doesn't it feel good, right? And what does that mean? And so I think there are a lot of little pieces that you have to work on with them to help them. With it, but I think they have lots of things that you could bring to bear, and as I said, they're well prepared to change some of their ideas. Not everybody actually, even in the end, agreed on that one. And I must say, I have done this with 8th graders in middle school. I mean, a lot of my work was in middle school, where 50% said the tiny bees didn't. I was floored when I walked in, and we had a long discussion. But part of my